So today we're going to have Gerardo Paz Silva from Griffith University talking to us about noise in quantum computers and hopefully how to mitigate it. Gerardo, please take it away.
Okay, good morning, and thank you very much, Chris, for having me. So I guess my name is Gerardo. I know many of you guys here in Australia, and I have been working on noise cancellation for a few years now. So I'm going to talk very briefly about what we have been done, what has been done in the field in the last few years, and what we have done in more recent times to overcome some of the limitations that let's say that existing protocols for noise cancellation had. So this has been really a team effort. I mean, locally at Griffith, I work directly with my PhD student, who is Tirawat, and two postdocs that are Yuan Long and Behnam, and they will be involved in the results or they are involved in the results that I will be presenting today. And as well, I also closely collaborate with Dr. Lee Norris and Professor Viola at Dartmouth College. We are funded by an Osmery grant from the Department of Industry, Innovation and Science that has allowed me to collaborate strongly with Chris at UTS, with Andrea Morello at UNSW, and we have some other collaborations across the ocean with some other US groups that are also interested in this problem of characterizing noise and compensating for it. So now let's start with the science, I guess. So the standard picture that we have is the open quantum system scenario, where you have a system or a qubit. It can be many qubits, it can be a qubit, and there is a bath. And of course, your system interacts with your bath, and this is typically captured by some Hamiltonian that maybe the bath has its own dynamics. There's a system Hamiltonian, and there is the system bath Hamiltonian that is the one in charge of coupling your system to the bath, right? There is also, you have the ability to control only your system by definition. You can also measure your system, and you can do not much else. And of course, you can track the dynamics of your system by measuring expectation values of observables. And these are given by the standard formulas from quantum mechanics. And as far as we are concerned, when we try to do, because our objective is to do, let's say, a quantum computation or maybe some quantum sensing operation, what we really want to ensure is that we can execute a gate. And so what we want is that we want to generate or design a control such that in principle, we can track or we can get the desired evolution of a given initial state or for any initial state in principle, right? And so what we want is that the expectation value of any observable that we have is actually very close to the one that would be generated if we were applying a very clean gate that we actually want to apply. Okay, so of course this is an old problem in the sense that this is basically at the heart of our ability to implement or hope to implement quantum computers and all these things, and there are many approaches to it. So the dream, of course, is to have a protocol here in this red dot where we have the absolute best quality, but we don't have to know anything about the bath or about the system or anything. Of course, this is just a dream because it cannot happen, and there have been several ways to try to overcome this sort of to get some good quality control, but maybe with only few assumptions on the bath or on the noise. So dynamical decoupling, for instance, is one strategy that really only assumes very small things, maybe that the bath is sufficiently slow, and it applies a sequence of unitary pulses. And the idea is that if you apply your pulses or your control routine in a particular recipe, then you can get high fidelities for not only for the weighting gate, but also even for a targeted gate. And so here I'm grouping things like the so-called dynamically corrected gates or composite pulses, which have been around now for a few years. On the other hand, we have optimal control. So optimal control demands more knowledge of your system, of your noise, or your system and bath, but can get better fidelities. So basically, it assumes some knowledge from the bath, as I was saying, and then identifies certain cost function, and it minimizes or optimizes your control in order to get let's say maximize the fidelity of certain operation. Of course, the issue is that some of these of the assumptions that are needed for optimal control are actually can only be assumed, in the sense that they cannot be measured directly. So things, for instance, like trying to say that the state of my bath is a thermal state with a fixed temperature or a given temperature, and maybe that I know that my bath Hamiltonian has a particular shape or a particular mathematical form, or even that the system bath operator, the system bath Hamiltonian is described by certain bath operators, then these are things that I cannot really directly measure if I only have access to my system, right? Which is kind of a key part of the whole open quantum system paradigm. Of course, you can say that that certain things can be, we know our systems, our physical systems relatively well, and maybe we can know part of this information. But by the very definition of an open quantum system, it's not really possible to know everything about the bath, right? So there will be always some degree of freedom that is acting there that we cannot really characterize, right? Or even touch, right? On the other hand, there are certain, the key question is, of course, if there are optimal control protocols that can use experimentally accessible information. And this is where we want to be, right? So we want to be in a situation where we can use our system to characterize certain relevant information about our noise or whatever is described in our quantum system in such a way that we can actually use the optimal control tools to get our very high fidelity gates. And so I will hopefully convince you that later on that this type of information comes in the form of bath correlators, and in particular a certain subset of the possible bath correlators. And so this will be really our strategy, right? Our strategy will be to characterize the noise that is affecting our system by using only measurements and control over the system. And this is key, right? Because you can imagine that in the typical scenario that we have, right, we are applying your control here in green, and the noise is, of course, sending some other mixed signals. And our qubit is really confused at the beginning of the story. And so we want to say, well, given this situation, what can we do? What sort of signals can we apply for the green speaker? And what measurements can we apply, can we execute in such a way that we can get some characterization of the noise? The hope, of course, is that once we have this characterization of the noise, which I will hopefully specify in a few slides, we can then optimize our control in such way that effectively the qubit starts feeling only a very small component or a very, let's say a weakened version of the actual noise. And of course, we can get in that way we can get better fidelity, let's say, for our gates. Okay, so this is, I guess, the general philosophy that one wants to apply. Of course, this is nothing new in the sense that you can even use, noise canceling headphones work around this principle, right? And this may be as old as Sun Tzu's node dienemy, right? In quantum mechanics, or at least for quantum control, we have not been the first to propose it. Of course, the idea has been around for many years, and it has been indeed let's say the essence of many of the existing optimal control or quantum control routines. The key point, or the key step, I guess, that we want to take is to actually be able to build a full set where we can eventually characterize or get a full characterization of the noise, which is relevant to the control and uses only system only operations like measurements and gates. Okay. So that being said, we have to go into the math to actually understand what is it that we mean by characterizing the noise and optimizing and so on. Okay, so let's do the typical thing. So the first thing that we want to do is separate the effect of the control from the effect of the noise. And so the typical thing we do in this open quantum system language is we go into the toggling frame with respect to the control. And so we essentially separate our system bath unitary, which is the one that is executing all our system and bath dynamics in the open quantum system. We separate it into one that depends only on the interaction Hamiltonian, that I use UI in red, and we have the element of the control. And this Hamiltonian will be your working horse, right? It has some key features. Then the effect of the control is captured by these switching, let's say, switching functions or control matrix elements, depending on which paper you read. But the important thing is that here, these time-dependent functions contain all the information that there is about your control. Whatever control you choose, there will be some transformation or there is a particular form or shape for this YAB of t. On the other hand, this BB of t can be thought either maybe it's a classical noise process, or you can think of an stochastic process, maybe if there is no quantum bath, or you cannot, if there is a quantum bath. On the other hand, you can think of it as the interaction picture of the representation of the bath operator with respect to the bath dynamics. Okay. So the important thing here is to identify these two elements, right? Switching functions and bath operators that are possibly time dependent. And of course, once we do that, then we can say, okay, what is the effect of doing this? And what is the effect on our equations of the things that we can measure? And the effect of any expectation value is then that we can write our expectation value in this way. So there are two things that we identify immediately here, right? The first one that I'm highlighting here is this operator VO of t. So this operator is very special because it's the one that if this operator was not here, for instance, right, it was identity, you can immediately say that this guy, the ROS of t, could be just be the execution of some gate, it would be the ideal execution of the gate at that, right? And so it becomes clear that VO is actually what contains all the effect of the noise. It's all wherever is where all the bath operators are appearing actually. And so if we wanted to do, for instance, a noiseless implementation of some gate G, what we would like to implement is a control such that the VO of t is as close to identity as possible, and that the ROS of t transforms according to the gate, our gate that I want to execute, right? And that is really what we want, right? At heart, right? Get a gate that is good enough. And so this also implies that we have to understand VO a bit more in a bit more detail. So if we expand it in some either a dice or a cumulative expansion or whatever you want, whatever you are more comfortable with, what you realize is that really this VO of t operator, which we can call a propagator if you want, is really some combination, right, of these integrals or time order integrals of this form, which really which are of different m. So they are time order of different and let's say of m concatenated integrals or ordered integrands. Sorry. And you see that again, the two elements that were appearing before appear now here prominently. So we have the effect of the control, which is captured again by these products of now of the switching functions or the control matrix elements. And we have the correlation functions now of up to an order m, right? And so this is formal at this point. This is just a way of you can always show that you can write it your dynamics in this way. More importantly, is that you realize that when especially for m, when m is larger than 3, and you are looking now about a three body correlators or the 3 in your whatever perturbative expansion you choose, you realize that importantly, not all the orderings of the times will affect the dynamics of the qubit. And this is something that you can formally show if you write your higher order terms and whatnot. And what really appears is, and this is what I'm highlighting this L here, which is just to say that I only have linear combinations of certain permutations of the time arguments. And so this is the first let's say the first observation, or the first thing I want to highlight, is that my qubit is not capable of seeing the full bath, in the sense that it only, first of all, it only cares about the bath correlations. It doesn't care about the bath state. It doesn't care about, I mean, clearly, so that bath state is clearly entering here, this bath correlator, but it doesn't care about exactly about the bath state or the bath operators or even the bath Hamiltonian. It only cares about the bath correlations that they can generate. And that is the first observation. The second observation is that the qubit cannot see all of these bath correlations. It only sees certain linear combinations of them. Perhaps the most well-known model that we can, that is perhaps more familiar for everyone, is the case when you have, a dephasing qubit and you're applying maybe some pi pulses to it. And here, then you would say, well, it's a dephasing Hamiltonian. So you have the typical Z operator, and then you have some bath operator, which can be maybe can be either a stochastic process or maybe a quantum operator itself. And if you were to compute, let's say, the expectation value of x, of an operator sigma x, you will see that this thing is just is a factor that is an exponential factor that represents the decay of the coherences, and times the exponential, right, the expectation value, sorry, of the same operator sigma x at time 0. And this element here in the exponential has, again, this is what represents our VO essentially. It represents, or when it's a real manipulation of the VO, but the important thing is that it captures, again, the type of integral that we have been referring to. So there is some time order integral, right, where you have the switching function, this y of t twice, right, because here it's assumed that it's a Gaussian process for simplicity, right? And of course you have here the correlation functions. And you see that what we have access to here in this case is just access to the commutator of the correlation, anti-commutator, sorry, of the correlation functions. And you see that indeed this is basically captures this observation that not all combinations appear, and let's say free appear or affect the qubit. And this is to say that if you perhaps are more familiar with this noise model, is to say that a qubit under pi pulses or under pi pulse control that generates this sort of interaction picture Hamiltonian cannot see the quantum features of the bath if it's, or of the noise if it's, let's say if the bath is a noise is Gaussian, which is the case, for instance, if you have a, a bosonic environment with a thermal state. Okay, so hopefully this sort of transmits the idea that characterizing the noise for us is really being able to know what are these linear combinations of bath operators and or expectation values or bath correlators for different times and so on, right? So if we had this information, then we can do many things, right? So if we're interested, let's say, in control and decoherence suppression, then what we would like to know is if we can know the CNOs or enough about this linear combination of bath correlators, we could in principle think of, okay, let me minimize the values of these integrals. And as the previous case of the dephasing showed, then we can get, for instance, like very low decoherence, for instance, if we could minimize the I, right? So then the smaller the value of the integral in the exponential in the previous slide right here, the smaller this value is, right? It means that the more suppressed my decoherence is, right? And so this is one of the possibilities, right? And this will, of course, lead to better gates, which is something that we always want. And on the other hand, we can do other things. We can use this information about this correlation function to extract or to learn physical properties about the bath. We can do, for instance, bath thermometry. If you have, let's say, a thermal state for some bosonic environment, you can do thermometry, and we have done this. Well, we and other people have done this in recent years, at least theoretically, and some people also experimentally. And you can do in generally any parameter sensing that is relevant to the bath, right? If you have some model for your bath that is described by some physical parameters, by knowing these correlation functions, you can start to distill part or infer some of this information, okay? However, our focus for this talk is this one. Our interest is actually just control and decoherence suppression. And so this of course, what this has led to is to this need to characterize these correlation functions. What has led is to the birth of these quantum noise spectroscopy protocols. And in a way, quantum noise spectroscopy is really just this, right? You are trying to characterize these correlation functions, and in some very, let's say, in some hand-wavy way, you can think about this as a time-resolved tomography of the open quantum system dynamics. If you have this information, you can do the great things that we can do, we mentioned before. But of course, the important thing is how to do it, right? So it seems that it's a natural question, but how can we actually do it? So these protocols tend to be just, if you read the papers, you realize that this is really a recipe that gives you a set of initial states, some set of unitary controls that you can apply, and some set of measurements. If you combine all of them, you get some sort of tensor product structure. Then you can get a bunch of expectation values for each of these combinations of initial state, control, and observable. And the idea is that if you have you can design some classical processing routine, then it is in principle possible to infer this, the information about the linear, about the bath correlations, or this linear combination of bath correlations that we actually seek. And so the key question, however, is how to do this. And what the main obstacle is, say, well, given this recipe, right, of giving access to these integrals that we were having before, which once you understand a bit these protocols, you realize that in reality, all this point of injecting different initial states and measuring different observables are really just a way of isolating all the different integrals that contribute to the dynamics. So the problem, once you strip it out of the quantum mechanics, it is actually a problem of, it's a classical estimation procedure, right? You want to, given access to these I's, and given your ability to change or manipulate these switching functions that depend on your control, right? Then the question is, what can you infer about these correlation functions, right? And this is the whole point of this type of protocols. And so the key to achieving this, right, more in terms of the mathematics, is the so-called filter function formalism. And so it's really a way of rewriting our integrals in such a way that they become friendlier. So for instance, if we had an integral of this type, which is like the typical set of second order integral that we would have, where there are, again, the two switching functions and the correlation function, I can move into the frequency domain and do a Fourier transform. And let's imagine here that the noise is stationary. And so if I move into the frequency domain, what I have is that this is just the power spectrum of this associated to the correlation function, just a Fourier transform of this correlation function. And when I rewrite my integral, then I have this object here. There is this double integral involving the switching functions and of course the exponential factor. And this is what is known, or what we call, the filter function. This was pioneered by Kurisky, and we generalized it later to a more general decoherence, or for a general decoherence scenario. And the thing is that these objects have two important, or a lot of information in general, not only for this integral, but in general, of course, a model, like an arbitrary model, you can imagine that it has a collection of many of these integrals, right, that you have to analyze. And but the structure is always the same: a filter function, maybe of a higher order, and a correlation, or the Fourier transform of some correlation function, which can be a multi-body correlation function. In this case, I'll just show them for the one for the second order correlation function. But you can imagine that the structure just keeps going and going in principle for any of your perturbative, any term in your perturbative expansion, let's say. And so there are two, this overlap integral has a very nice structure, and it actually is very convenient to understand for understanding two things. The first one is that you can understand what is the coherence suppression relatively well here, at least as far as unitary control goes. For instance, you can show that clearly minimizing the coherence is just minimizing these integrals. And because you have this sort of overlap structure, then you realize that really minimizing the integral is just a method of minimizing the overlap between your filter, which is something that you can control in principle with, by controlling your pulses, and the spectrum of the noise. And you realize also that the traditional, the well-known dynamical decoupling sequences are just sequences whose filter functions are very flat around the omega equals 0 regime. And so they have a very small overlap with noise that is heavy, let's say, or spectrally concentrated around the 0 frequency regime. On the other hand, you can flip the problem around. Then you can say, okay, so I can also try to learn about the noise, right? So you can imagine, for instance, that instead of having this green filter, which is in this case the filter from one of the well-known CDD1 sequences, which is basically the Haneko sequence, you realize that in principle, if I could move these green, generate different filters, right? Move this green peak, I could move it to the left or to the right. I could start getting really a lot of information specifically about this overlap between my spectrum here in blue and all of these filters, right? So I do an experiment and get information about the noise here, change my control, do an experiment, get information about it here, and so on. So you can imagine that, okay, in this dream scenario, if I could move this filter to left and right, I could essentially reconstruct my spectrum in very high detail, right? And well, this can be maybe achieved in certain super ideal scenarios or certain very specific scenarios. It's really not easy as it looks, right? In general, so when your filters, because of the constraints in the equations and in the control, actually look, maybe not as nice as these ones, and you cannot maybe move it as to the left or right as you would like, but they actually look more like the red line. There may be variations of this red line. And this is because, of course, the constraint that your controls and your equations yield. Moreover, when you have multiple, your model starts becoming more realistic. Maybe you have multiple axes. You have not only Gaussian noise, but non-Gaussian noise. Then you have to deal with many model complications. You have now multiple of these integrals that you have to analyze simultaneously. You have multiple dimensions. You have to deal with linear combinations of filters that look like this. So things become, let's say, murky, right? And the problem essentially is not easy. And then you have to really analyze as you go into a very deep analysis or very detailed analysis to be able to extract the information that you want. And so indeed, this has been the objective of many papers that have appeared over the recent years, that essentially try to generalize this sort of simple observation that I was just mentioning below or before into increasingly more general models, right? So we go from the simple dephasing model that we have to much more general things. And so now we have, for instance, that we can reconstruct a spectrum for an arbitrary noise, Gaussian noise, for instance. Then you can do, when your noise is non-Gaussian, you can also reconstruct these sort of things. When you have multiple axes, then you have multiple spectra, and then you can still reconstruct all of them in the right regime. And even if you have, let's say, something like a noise that is like something like a random telegraph noise, you can still reconstruct the let's say the Troya spectrum, which is the third order correlation function for this process, for instance. And so these are all things that have been done. And sure, when it seems like if you just keep working hard and harder and harder, then you will get there, right? And you eventually get, increasing more powerful protocols. And sure, that seems to work, right? However, to be honest, the truth of the matter is that you would like is really a full general protocol, right? Which is capable of addressing multiple qubits, noise in all directions, non-stationary noise, non-Gaussian noise, quantum or classical noise, arbitrary, you deal with arbitrary control, be able of including control errors, for instance, in your model. And this would be the dream, right? But the truth is that we are far from that. So all these protocols have maybe improved a bit in all of these directions, right? In all of these, let's say, criteria. But the reality is that we are far from the final objective, which is this sort of all-powerful, let's say, assumption-free, or let's say, and with less assumptions as possible, quantum noise spectroscopy protocol. So this is not to say that the current protocols that have been there have been not successful. Indeed, you can see that these have been many of these protocols have been tested and experimentally verified by multiple experimental groups around the world. So the group of Andrea Morello, the group of Mike Bierchuk, the group of William Oliver, many times supported by Lorenzo Viola's group in the theory side, they have achieved this sort of demonstrated all of these protocols. Unfortunately, mostly they have been verified when you have injected noise. So that is to say, they generate some artificial noise, they throw it into the, they apply it to the qubit, and they apply it simultaneously in the spectroscopy protocol, and they verify that indeed they are getting something like the injected noise, right? However, none of these protocols has closed the loop in the sense that what they have not done is say, let's just take the noise that is native to the system, characterize it. I mean, maybe that step has been done, maybe in this Nature Nano paper, and more recently actually in a spectroscopy paper by Morello group, right? Spectroscopy characterization that the Morello group did on the qubit. They can characterize the spectrum. However, what has not been done is the next step, which is, okay, let me use that information to optimize maybe a gate or maybe a waiting time. Perhaps the best example of what can be achieved, and maybe it's a bit of a hint of the power of this sort of approach to the problem, is this paper, which I was very happy about I think it was last year. And so here what they did is that they by different techniques, they were able to characterize, and also by previous knowledge, they were able to characterize what is the noise, the dominant noise in their ion trap. And so once they identify this, they say, okay, their spectrum had, let's say, a minimum at a given frequency. And so what they did is they said, well, let's increase our coherence time. And how do we do it? Well, they chose a sequence that had a filter, which only had a peak around the point where the spectrum was minimal, where they had where the spectrum has this tip. And in that way, they achieved this amazing coherence time. So this is a bit of a flavor, I guess, of the motivation to why these sort of protocols can be super useful, of course. And so maybe hopefully this is some food for thought for experimentalists when they try to or want to improve their gates in the future. Of course, as I was saying, their objective, which is getting to this sort of super general protocol, right, is still not there. And so last year we were thinking about it and said, well, we sort of have a way forward in the sense that we can just keep working, keep doing detailed analysis, and eventually you see that you will get there, right, with a lot of work. And in principle, things can be done. However, to be honest, I was a bit sad because it seems that this was like this very detailed manual work of analyzing the problem. And there was a bit of there was something missing, in my opinion, at least, that could push us beyond this the current status. And the main issue, of course, is that when you have a given control setup, right? Maybe you have instantaneous pulses, or you have your pulses have some Gaussian profile or some Slepian profile, you name it. And given the mathematical constraints that are given from quantum mechanics, then deconvolving these integrals is not a trivial issue. And of course, when maybe in a sketchy way or in a sort of cartoonish way, what you have is that you have some expectation values, you have some control, which you have used to use your to implement your QNS protocol, and you can. This gives you a characterization, right, of your noise, which is constrained by the control that you have available. And then you push it in the other direction. You say, well, clearly, if I have this, given this characterization, if I can apply again a control that looks like the one that I used for my QNS, then I will predict some expectation value. And clearly, because you're essentially using the same control, the same type of control, then your predictions will match what you measure. And this is great, right? The problem, however, and this is, I guess, not only a problem from the theory, but also at the experimental side, I guess is behind the main reasons why this sort of closed loop, this loop has not been closed, is that when your control is not the one you used for spectroscopy, then things are not so clear, right? Because in principle, right, your noise has a full characterization, all your bath correlators. And if you knew all of this, right, if you apply and you put your field, your switching functions corresponding to an arbitrary control that you applied, you will get some value, right, or some expectation value. On the other hand, if you do the same operation with the one that you have obtained, the characterization that you have obtained via your QNS control, then you would see that the expectation value that you predict is not guaranteed to be the one that the actual experiment sees. And the reason is that this is, of course, constrained. This is limited information. It is not all that the qubit can see, for example, if you have certain very strong constraints, let's say, on the control. And so in order to ensure that these two things match, then you have to start saying, okay, I have to start adding extra assumptions. And so one of the things that happens, for instance, in the so-called frequency comb spectroscopy protocols is that you have to start to assume, for instance, that your spectrum is smooth, for instance. And that is pretty smooth, that there is no, for instance, there is no hidden peak and so on. And that is, for instance, that it has some unknown, for instance, high frequency cutoff. And all of these assumptions actually add to the complexity, or the success, let's say, or the applicability of your protocol. And this is not a situation that we like, right? We would like to really overcome this. We would like to have a situation where we can actually predict that the information that we can access with the spectroscopy is good enough for us to just use that to predict, right? And so the key observation is this, right? So we were thinking about this and we thought, okay, what if we introduce the control into the problem from the very start? So within the formalism, we introduce the control constraints directly from the start. So initially we were not doing that because, of course, the mathematics becomes more complicated and you have to start making some, say, oh, my protocol would apply only for this type of control if I do the analysis in one or the other way. But maybe that was the key, right? Maybe that is the key. What if I just put my constraint from the beginning and then try to analyze the problem with that constraint in place? And so the key observation is that if you have any constraint control, let's say whatever your, the type of waveforms that your digitizers can give, or any experimental constraint that you can think of, then it actually implies that the type of switching functions or control matrix elements that you have certain structure. So each of these guys has a structure, and the task then becomes, okay, so if they have this structure, then you quickly realize by looking at the equations that in reality, if we wanted to predict the behavior of the qubit, we only really need to learn what are the components of the noise that are relevant to that structure. Of course, this is all in quotation marks at this point, because this is sort of the intuition, but it's perhaps not so clear how one can do that, right? And so the task is to provide the mathematics that will allow us to identify this structure. And then the key thing is we just really need to choose an appropriate representation for a given control. And this is really the essence of it. And what I'm going to argue in the next coming slide is, well, how do we choose the structure, and what is the correct language in which we can do this? There are some key ingredients, but at the end of the day, what I'm going to hopefully tell you is that given a control, if you choose your appropriate representation, there is a lot to win. Perhaps And there will, of course, be some sorcery here, but eventually we'll get to the result. Okay. So maybe give you a bit of more of an intuition of why this could be that way, right? So imagine that you have this situation where your control is band limited for some reason. The type of controls that you have is such that that the filters are always band limited, in the sense that they become zero after given big omega, right? Some, let's say, cutoff frequency, and and all you need for your dynamics is this integral here, right? So what you quickly realize is that if you have this sort of structure, if all the filters that you can generate are always band limited, then the spectrum here outside could be whatever you want. And because the overlap will always be extremely small, right? Then it really doesn't matter what it is outside of this region, right? Here or here, right? And so in the end, what you truly need to know is only, or the dominant piece of information that you need is actually the spectrum in the region of interest that is in this sort of between these two lines, two dotted lines. Okay, so this is, of course, what is known in signal theory or in signal processing theory as Slepian sequences, and this has been exploited for, let's say, also for QNS, for quantum noise spectroscopy in Lorenzo Viola's group at Dartmouth, and also by Mike Pierchuk's group at the University of Sydney. And so, but here the key thing of this is, this was a very celebrated work in signal processing, this Slepian structure, is that the Slepians were built in a way such that their filter function representation, or their representation in frequency domain, was band limited. Okay, so they're Slepian, they're special as far as the frequency domain is concerned. Okay, so you can start thinking, okay, so that's good, but my control doesn't have to be that way. So my control can have many ways, many shapes, right? It can be, maybe it's instantaneous pulses, and maybe it's just some, some arbitrary pulse profile that can be, I don't know, a Gaussian or some other shape that I want, right? And so maybe what we can do is invert the direction of the arrow. Instead of doing what Slepian did, which was find the control sequence such that it was well represented in the frequency domain, what if we found the space or the representation in which the control that we have is actually well represented? And this is the switch in the way of thinking that we want to apply and hopefully exploit in the next coming slides. Okay? So in order to do this, to be able to achieve this, we will need to do three key ingredients. So the first one is that we need a flexible language to do this. So instead of having the Fourier transform as our key ingredient, which is what was used in the standard frequency domain formalism, we would like to do something more. We would like to find a space, in this case there is phi alphas, which are some arbitrary space for a representation to represent the function y of t. So a neat way of doing it is the so-called frames, which are nothing else but a generalized over complete basis, if you want. They obey some they are defined via some mathematical equation, and they are great. They have been they are extremely important in signal processing theory. They have some very, very cool robustness properties. They have been used also in tomography, in quantum tomography, and they are great mathematically. They are extremely powerful, and they are very friendly and very intuitive to work with. The important thing, however, of this language is that it provides a way of uniquely writing any function in terms of this frame. And of course, there is some other mathematical object that is called a dual frame, which and the key point, of course, is that you can always write this, the y of t represented in terms of a frame, and it's dual. And the important thing is that these coefficients are unique. So this, of course, this implies is that this guy here is unique as well. And so this is component one. Basically, we have learned how to express any function in some arbitrary space. And of course, we have complete freedom of choosing a frame. And this is the part where this is one of the key elements for what we will do. So we can learn how to expand any function into some arbitrary space that we can build. Okay, so this is item one. And the reason why we use frames is basically because they are, at heart, QNS is a signal process estimation problem. And of course, we want to eventually down the line exploit many of the properties that frames bring along. The second component is a change of point of view in how we write our equations. So In the frequency domain, as we were saying a few slides ago, we write our time integrals into these frequency domain integrals where we have this, again, this overlap. And we had that all the, this was just a Fourier transform, right, of the correlation function, for instance. And this was simply, you know, the time order integration, right, where we had of the switching functions y of t and y prime of t prime. Okay, and so that was great. I mean, we knew we used that very well, etc. But when I started thinking, okay, so really what we want is to really have the most flexibility in what we can control. So what if we, instead of putting all the time dependence that we have in the filter, what if we could just put it here in the object that contains the information about the correlation functions, and let's call this as alpha of alpha prime. So this is just a rewriting of the equations where we have used this relationship, right? We have assumed that each of the switching functions that we have can be written in the frame, and of course here we have just rewritten that equation, right? The important thing here, or why this is important, is that now you can start demanding things on the control. And this is, of course, very natural, because that control is what you can actually, you know, even though I'm using the same word, it's a you can actually control. And so in a previous point of view, right, we were starting to, when we were for the spectroscopy protocols, right, we were demanding things on the representation in frequency domain of the correlation function. But of course, a demand of something that you cannot control is an assumption. And then if it's not satisfied, then the whole thing breaks down. However, when we moved into this language, we say, well, this object here is something that we want to estimate, but I don't want to assume anything about it. So every assumption that I want to put in place, I want to put here on the control, right? On what signal I can put into my signal generator, etc. And so this is the second element, right? We are writing things in such a way that all the assumptions will now go here. And this is where the flexibility lies. Of course, there will be more of them, of these unknown parameters S alpha alpha prime that we'll have to deal with. But it doesn't matter, right? Because our objective is not to understand what the correlation function is to understand what is the elements of the bath, or what is the relevant information about the bath that influences our dynamics. And this is the key. Of course, up to this point, we have just changed our language, and that's it, right? We still have, if you remember, many of the issues that came from the frequency domain estimation of the spectrum is that we have an infinite integral, and our objective was to infer S of omega by trying to somehow deconvolve these integrals, right? So when we change the language here, we really, so even though there is a bit of a slight change of point of view, the mathematics is still equally problematic, right? It's still, if we wanted to estimate this guy, it's still a deconvolution in principle of an infinite integral, right? Which is not even, so it's formally doesn't have to be even discrete, etc. Right? So the problem is still there, right? However, now we have the ability to demand things on this expansion, right? And so what if we demanded that it was finally supported in some frame? And so this is the third ingredient. Imagine that you could build a frame that you can associate to given some control, right? And you can build a frame such that each of the switching functions are just compactly supported up to some very small error. So what this is telling me is that so my switching function, any switching function that my control can generate, is expanded by only a finite set of frames, right? In this case, n sharp. And this finite set of parameters describes all the possible control that I can apply. So if I know these parameters, in this case, n sharp of them, I can completely describe what is the control, right? And the trick is to choose my frame in such way that this error is small, okay? And this would be the third ingredient, right? Building the frame that matches your control. If this can be done, then let's see what happens. Well, the main thing is that now I can rewrite my integral, but with the key difference is that now the summation, which was an infinite summation before, right, now becomes naturally finite. And this is in the same vein of what happened when we had the Slepian example, right, where the integral over frequency was basically reduced to the integral over some region of space. And this is exactly what we have achieved now here, but in the space in the correct frame, right? If the frame can be built, then in the correct frame, this integral takes this very simple form. So there are two main conditions here, two main consequences here. The first consequence is that it tells us that these S alpha alpha prime, or elements that are the representation in this frame that the representation of the noise in this frame, are all that we can know about the system, about the noise. So basically this says, well, if your control capabilities are those, all that you can know are these finite set of S operate or S alpha alpha elements, right? And in principle, if you sample or a sufficiently large set of filters, right, which is just, if you recall, it's just a different set of control sequences generated from the same control that you assume you start with, right, then you can, in principle, sample all of these guys, right? Or at least, yeah, so you can sample all of these guys. On the other hand, if you look at the optimal control problem, then this equation tells you that this same S alpha alpha prime for alpha alpha prime up to n sharp is all you need to know in order to predict the dynamics and do optimal control. Because there is really, if you have a control where it's saying all the information that is important is this, right? And there is nothing else, because your control is now being represented in let's say, in an efficient way or in a compact way in some sense. And so optimal control is not just a matter of optimizing over my choices of controls, which are picked from from the control assumptions that we start from. And so what we have achieved then is that we have leveled the ground, or we have put, we have made the optimal control in the QNS protocol, the control center QNS protocol, equivalent in some sense, or the dual to one another directly, right? And so what we have now truly achieved, right, is that first of all, the problem is finite in the sense that if you choose your frame, then it has n sharp of these elements, then you only have to worry for each integral of some, or in this case for the order 2 integral, for instance, you need to work of n sharp square of them, right? Elements of pieces of information. And so this is a finite problem, this is element 1. The second one is that now we have, when we apply the full characterization of the system, which is the one that is the ideal one which we cannot access, right? With a constraint control, and the characterization of the noise associated with the control that you can have, they both give the same prediction, and which is actually the real prediction, even if you apply the control that you have for the QNS protocol on arbitrary control within the same family, right? So the key point was that when we input right the control constraint, or we input the information about the control, which is done through the frame, right? In the problem from the beginning, now all of the problems or all of the, let's say, uncertainties that we had before, and when we were trying to force some control to extract information in the frequency domain, right? All of those problems disappear because we are already in the constraint limit, in the constraint setup. And it is exactly the type of information that you need to predict your dynamics when you have this constraint control setup. Okay, and this is, I guess, the key of the philosophy, right? Achieving this this result in the blue box. So this is, let's say, this logical step in the blue box. Okay, so let me now illustrate to finalize, I guess, or almost. Let me illustrate this by two examples. The first one is the case of instantaneous control. And so in here, what I have is, imagine that I have a total time from 0 to t, right? And between multiples of, and I can apply any instantaneous pulse that I want at a multiple of some fundamental time or some switching time tau. And so t1 is tau, t2 is 2 tau, and so on, right? And the question is, of course, how do we apply this thing, right? So the first thing that we identify is that we have to study the structure, right, of the switching functions. And we realize that the switching functions are just, piecewise constant functions that can take values within the interval -1 to 1, right? And they, given your choice, then each of these y of these looks like this. So this sort of puts, this sort of guides you, and you say, well, given this, then I may as well use a digital basis. So I can use the Walsh basis. So, but you can, here for our purposes, we use the Walsh basis for historical reason, basically because, but we are essentially generalizing some work. We will show that essentially what we do, right, in the example, in this small example, is to generalize a protocol that was introduced by Capellaro and Alex Cooper some years ago to reconstruct time-dependent signals in the Walsh domain for when you had using a QUIT as a probe. what we're going to show, or what this example shows, is that basically by just changing your point of view and everything, you can extend this protocol to an arbitrary space, to an arbitrary correlator, not just, let's say, the signal or the mean of a signal, but also, let's say, order 2, order 3, and 3-body and 4-body correlators, etc. Anyway, so we're going to use the Walsh for our protocols, or this is what we use in our numerics, because these historical reasons, but you could have also used the hard basis or an impulse basis if you wanted, and the result would be the same. So it's just a matter of a language at this point, okay? And the idea is that you can then, you can show that, of course, any of these functions can be then expanded in the Walsh basis, which is a frame, but of course, when the frame in question is also a basis, then it becomes self-dual. So you only have, you can just show that you can expand it in this way, given some appropriately defined inner product. And if we do our dynamics and we test it, let's say, for a dephasing model, or kind of in the same vein that I illustrated in the beginning, where we know our equations and are very simple, right? Then we recognize that, of course, the expectation value of any observable is just a function of two types of correlator functions. The one that depends only on the anti-commutator, and one that depends on the commutator, right? And so let's call these quantities represented in Walsh as S plus and S minus and N prime, okay? So one can show that if you implement a protocol for spectroscopy where you essentially measure the X, Y, or Z and prepare in any of the Pauli eigenstates, and then you apply sequences of pi pulses and pi by 2 pulses in the Y direction, then you can extract all these quantities, these S plus and N prime and S minus and N prime. And what I won't go into the details of what exactly sequences that you have to choose, and you will be able to find them in our paper later on. The idea is that you can reconstruct things. And so in particular, I want to point out, this is for instance, an example that we did where you have essentially a random walk process, right? Where your correlation beta here, where your correlation function is the minimum over T and T of T and the 2 coordinates. So it's clearly a non-stationary process. And then we have modulated again, given additional modulation by some oscillatory function. And the idea is that the left-hand side here shows the correlation function as it would be in theory, right? And the right-hand side is what happens when you have your total time and you have divided into 16 intervals. So you see that the information is clearly not complete, right? And so the left-hand side can be expanded into a full, an infinite expansion of our Walsh functions. However, the one that we recover is actually just expansion over the first 16 of them, right? Without control. The important thing is that as far as the control, if we are only allowed to apply sequences of pulses or pulses at these fixed times that we were mentioning, right, then they are equivalent. And this is the key part, right? This sort of transmits the information that we were trying to, or the point that I was trying to make before, that if my control is constrained, I only need to reconstruct what is relevant to that control, and that is all, right? And the frame has simply allowed us to formalize this statement and be able to use some clear relationships to distill this information. Of course, this is not to say that we can only use this for estimating or to improve or predict gates, right? We can actually still, even though we cannot access, or we will not be able to access the full correlation functions in time domain, we can still extract physical parameters about the back. So this is a cute example where you have, 2 oscillators coupled to some quantum system in a dephasing model, let's say, and each of them is a typical, the time-dependent Hamiltonian is a typical element, right, of a bosonic environment, or let's say an oscillator system, right? And then you can assume that they're in some thermal state. And what you can show is that you can reconstruct a corresponding correlation function as well, using just a probe as a qubit. In this case, of course, we are interested in the minus or in the commutator of the bath operators, which are the ones that are perhaps have the quantum nature of the bath itself. And so when you combine the quantum and the classical, the symmetric and anti-symmetric part, you realize that you can actually use that information that we reconstruct, even though you're reconstructing it in the Walsh dimension, in the Walsh frame, sorry, then you can still use it to estimate physical parameters. In this case, you could estimate, for instance, the coupling, the natural frequency of each of the oscillators, and even the temperature of the oscillators, but just using the single probe. So this is just to say that even though we are working in a different space, the information that we access is still good enough to learn about physical parameters of the path. Okay. So, and clearly, of course, the more resources you invest, the more, the better estimation of the parameters. But this is perhaps a bit of a side note at this point. Okay. So the important thing is that we can now characterize non-stationary noise, for instance. This is something that also that is non-show here, is that we can actually extend the protocols that we have to multi-axis, non-Gaussian noise, and this can be done simultaneously, which is something that we were not able to do in the frequency domain. The final thing that I want to show you guys is the ability to do non-instantaneous control, or spectroscopy using non-instantaneous control, which is one of the main questions that I had whenever I was presenting spectroscopy a few years ago using this instantaneous control. So imagine that you have your pulses are now just Gaussians, right? And applied at a certain point, right? And the idea is that again, we can do the same, right? I try to identify the structure of the control. You realize that all the switching functions are linear combinations of cosine and sine of this form, right? And so instead of having a given frame, as we had in the previous case, we have to build our own. And this is where the frame, formalism comes very handy, because we have all the frame, the frame mathematics. We can build our own frame, and we are guaranteed that it has all these nice properties. And this is what we do, right? And this is just to give you a bit of a flavor of what we can do, right? And the key thing is that when we build this artificial frame that we have, what we have is indeed, we still get the finite element, but we have now the error that we were mentioning at the beginning, right? And this error, depending on what frame you choose, can be made also very small, as we were saying before, right? And so we can show, for instance, that if I choose 3 angles here, 0, pi by 2, and pi as my elements of my frame, then I can get a very small error, 10 to the minus 3 for n is equal to 3, 10 to the minus 4 if I choose 2 more angles randomly there. Well, not randomly, but with some structure. And the main point is that if I increase the size of my frame, of the elements of the same angles in this case, right, eventually I will reach a point, or I mean, in the ultimate case where I pick all the angles, then of course the error is 0, right? Because my frame is actually my basis itself, right? Or my frame itself. So there is no, there is no error, right? But the point that I want to transmit here is that you can actually build your frame to be more and more accurate if you want, right? Of course, this just implies that when you are going to do your experiment to characterize this, you will need more resources to extract all these elements. But in principle, the algorithm is flexible in that aspect, okay? And so we can do again the same. There is some protocol to do the spectroscopy to characterize these the noise in this frame, and the details are really not important. It's just that you're using maybe the same elements of your frame to do the same angles for your frame, but also a couple of extra ones to get more information. And the point being is that you can extract the relevant information, the correct representation of the noise in this basis or in this frame. And what we gain is that we can now predict the dynamics as well. And the price you pay for not having an accurate representation is just some relatively small value, or close to 1 value, sorry. That depends on how good your frame is, right? The better the frame, the closer this guy is to 1. So some other things that I have not shown here, but also can be included, is that you can add control noise, and you can study also control noise, also within this frame formalism. What you can do is analyze the problem where you have not these sort of simple Gaussians that are not overlapping, but you have to just some arbitrary control profile that is just a mixture, or let's say a combination of non-overlapping control profiles, right? And you can, and at heart, really, this is this sort of idea of taking of learning with respect to a certain control is really behind the idea of, or behind the success, in my opinion, at least, of this work that we had with Akram and Chris a couple of months ago, where we showed how machine learning can be used to actually predict the dynamics. In reality, when I talked to Chris initially about this project, I was having this in mind exactly. And so I said, well, it has to work, because if I can do it on paper, the computer has to be able to learn it as well, right? And so I just want to point out these papers. It's a great read if you want. At least, maybe I'm a bit biased, but I mean, a bit it is. And finally, just to summarize, this is just to share that hopefully you guys have enjoyed this, but I just want to share our bit of our adventure into this noise cancellation, and basically it's how a change of language, a change of point of view, and the right choice of this mathematical formalism with which is this frame, right, with a control, is enough to guarantee great things. In particular, this sort of noise cancellation that we were seeking. And please look forward to this, to a paper that should come, hopefully be in the archive in the next week or so. Okay, thank you very much for your attention. And if you have any questions, I'm more than happy to answer. Thank you.
Yes, thank you, Gerardo. If anyone has any questions, just unmute yourself and ask away. While you're doing that, I can confirm Akram's paper is an excellent read. Thrilling. Gerardo, I wanted to ask you, so I think it seems like there's a very sort of natural progression in this field of relaxing assumptions and dealing with more and more complicated or complex, you might say, sources of noise. And then you showed some experimental results that I guess the point was to try to implement some of the protocols which characterize this noise. And those kind of, I guess, naturally lag behind the theory. And then I'm wondering, is there like another level where, you know, there's experiments that aren't specifically about characterizing noise, but, you know, necessarily characterize noise because they want to achieve something else, to, you know, something else in quantum technology, for example. Do you know like what level those sorts of results are at? Like in the labs where, or in the companies where we're building devices, what sort of noise characterization mitigation protocols are being used?
So I would say that so at the very physical layer, I guess, before you go into the let's say high level operations, I would say that dynamical decoupling is the most used let's say decoherence mitigation tool, and it's used at the base level. So you just apply a gate where if you're going to wait, you apply dynamical decoupling sequence, or maybe you apply one of these evolutions which are dynamically corrected gates, or you know, something along these lines. And these are great because they require low information about the path, but they're and they indeed improve your gate fidelities, right? Not to the extent that maybe an optimal control routine could improve it, right? So as far as I know, the experiment in which this has been done with most success is the nature photonics one I pointed to, is the one that where they characterize the spectrum, and they actually achieve this very long coherence time by just parking their filter where the spectrum was minimum, had a minimum. And this is how they got this 10-minute coherence time, right? Mm-hmm. But as I mentioned, I guess there has been no experiment that I'm aware of that characterizes the actual noise and then you know, improves a gate using the information. I know that in Andrea's group, for instance, what they did is that they characterized their spectrum, right? And they saw that there was a bump at some frequency. And what they could identify is that when they went and, you know, analyze their physical setup, their actual cables and connections and whatnot, they realized that this frequency was matching some line that was exactly the working frequency of some line that was going into their cryostat or something like that. And so, and they even show that if they had a better, so they could attenuate this noise, they could see, and then they could rerun, let's say, the spectroscopy. They saw that indeed the bump or the height of the bump could be reduced by physical methods, right? By just, you know, this is the one that is noisy, let me attenuate it in some clever way that I'm not going to pretend to know, but and so they showed indeed that the bump could be reduced just by just knowing what it is. So that would be not like an active way of controlling, but actually knowing, you know, identify what the physical source and dealing with it directly, right? But the dream of implementing this thing in the full cycle of characterize and optimize, I don't think that has been done yet in an experiment.
Right. Thanks. Are there any other questions?
So thanks for this nice talk. Let me ask you a very annoying question.
Yeah, that's right.
So at the moment you have in mind that you have your qubit, let's say, and you apply a lot of different control pulses, and you learn more and more about the spectrum given those constrained pulses. Then you feed this information of the spectrum in some, let's say, classical optimizer that finds you a good control pulse to fight the noise. So I think that's nice. I guess the question is, why don't we just cut out the spectral information and the classical optimization? And if we already have to apply lots of control pulses in the lab, why don't we just adaptively or in a learning control way learn a good pulse without ever learning any effective models of the bath, but we just know that the pulse that we found worked?
Yeah, no, so I mean, yeah, so I guess, like, undoubtedly, right, there is like there will be a set of pulses that you have to apply to characterize the system, right? Even if you do it our way, which is the one of extracting spectral information, or if you were just doing, your experiment directly, right? So let's say there are n pulses that you have to apply, right? And you could do the same, right? You apply n pulses to get, let's say, a particularly good gate, and in your experiment directly, without even ever asking about what is the spectrum. The question is, of course, that once you know what your spectrum is, then you can, just by classical processing, design what is the perfect, or let's say the optimal one that generates any gate that you can have, right? So this is, I guess, my first, the first layer, I guess, of my reply. The second one is that it is true also that you don't have to even ever ask yourself what is the spectrum, even if your objective is to, to characterize the noise in some sense, right? Because, and this, I guess, what we did with Chris and Akram, is that you throw the pulses into the, in this case, a simulated dynamics, and then you have just a neural network that learns about it, but you never ask it what is that, what it learned, right? It just learned, and then there is an optimal routine that when you say, well, I want to execute this pulse, it will use that knowledge, and it will spit out what is the control that executes that knowledge, that gate, right? And so I guess there are these two levels of my, I mean, sure, the spectrum is just for us to plot things in some sense, but on the other hand, doing the characterization beforehand is much more flexible than just optimizing every time you're going to do a gate.
Right. I mean, I guess my answer to the first point would be that in practice, maybe it suffices to find two good gates for quantum computing, right? You don't need to do arbitrary gates. You just need a universal gate sets. But I agree with the second point. And maybe if you can learn something about the spectrum, you can kind of transfer this knowledge also. For example, if you have several qubits and you learn something about the spectral functions of one of them, and then you want to do some similar optimization for the next qubit, maybe it's reasonable to assume that it experiences a similar bath, and so maybe you can do it more efficiently. But it would be nice to have a kind of cost comparison between the two schemes to see in which case one wins and in which case the other.
Yeah, that's a good point. Yes, I mean, something that we can do in the future for sure.
Thanks.
Thank you.
All right, great. Well, I think we can end it there. So thanks everyone for joining. Thank you, Gerardo, for the talk, and we'll see you around when the border opens up.
Cool. Thank you. Thank you, everyone.